Okay, so let's try to solve our contract design problem. The problem that we want to solve is this one. Okay, I want to maximize my expected profit subject to IC and IR constraints. Here, I need to find two functions, one function as Q, the other function as T, or you can interpret that you need to decide the QT pair for infinitely many types. Okay, so in some sense, even if you have taken courses like OR or basic optimization, this would seem to be very strange because you have infinitely many variables and infinitely many constraints. Okay, so I hope you are feeling excited now because you're going to solve a problem that in some sense is very complicated. Our strategy, uh, however, is actually very similar to our strategy for solving the two-type problem. We're going to first show you monotonicity, which again means a high-type consumer would eat more, consume more. Okay, consume more. So we're going to show you that Q theta 1 would be greater than Q theta 2 if theta 1 is greater than theta 2. And then among all the IR constraints, we're going to show you that only the IR constraint for the lowest type is necessary. When you have two types, the IR for the low type is necessary. Now you have a lot of types, only the lowest type is necessary. Among all the IC constraints, we're going to show you that only those local IC constraints are necessary. Okay, so you don't need those global IC. All you need to worry about is that your choice is optimal locally. Okay, and then after all those reductions, we can use binding constraints to get an unconstrained problem. And then we will do something called point-wise optimization to deal with that unconstrained problem. So let's do it one by one. So our step one is monotonicity. And the thing that we need to do is exactly the same as in the past. As long as we have two types theta and theta hat, suppose we say theta is greater than theta hat, then we have the two IC constraints between the two types. Okay, type theta should prefer the contract theta to contract theta hat. Type theta hat should prefer the contract theta hat to the contract theta. If we add the two constraints together, we're going to basically get exactly the same thing as we did for discrete types. Okay, T would cancel each other, and then we put the two terms with the same V of Q together, and then theta minus theta hat would cancel each other because they are positive, so the sign would still be the same. And finally, because V is monotonely increasing, so if V of Q is greater than V of Q and theta hat, then your Q of theta would be greater than or equal to your Q of theta hat. Okay, so as a conclusion, if your type is higher, then the quantity assigned offered to you would also be larger. Okay, because this is a continuous type problem, we can also show you that this just means that your Q should have a positive or non-negative derivative. Okay, Q must be increasing or weakly increasing. So monotonicity, we have that. And then let's reduce our IR constraints. Suppose I have a type theta, which is not the lowest type. Okay, the lowest type is theta 0. Suppose my type is greater than that, then I have a sequence of derivations. First, I can take the IC constraint for the type theta with respect to the type theta 0. Okay, if I am of type theta, I should prefer contract theta to contract theta 0. Okay, so this part is your IC constraint. And then from here to here, you use the fact that theta is greater than theta 0. And finally, here, This is your IR constraint for the lowest type. Okay, so as long as the lowest type satisfies its IR constraint, then all the types would satisfy their IR constraints. Okay, this is again exactly the same as what we did for the 2-type or n-type problems. Okay, so we only need the lowest type IR constraint. Now all others can be removed. So now your reduced problem is here. Objective function the same, IC constraints the same, but for IR constraint you only need one. All others are redundant. Now we're going to reduce the set of IC constraints. Or when we say IC constraints, we are actually talking about global IC constraints. Okay, that's too much. That's too many. We don't need all of them. We're going to reduce them to local IC constraints. And our eventual goal would be to show that the set of global IC constraints can be replaced by the set of local IC constraints plus monotonicity. Okay, so let's try to do it. First, let me formalize what we mean by global IC constraints. This is our global IC, right? Let's rewrite it in another way. For each type of agent, I know that guy is trying to select a type theta hat to report, and by selecting theta hat, he is going to select the contract Q theta hat and T theta hat. So that guy is trying to select theta hat to maximize his expected profit, okay, expected utility. And my goal is to make sure that for the agent's optimization problem, theta is optimal. Okay, theta is optimal. So theta must be greater than all other values in S. All other values in S. If that's the case, then it's globally optimal. Okay, so it should be optimal for a consumer to report his true type. That's global IC constraint. Theta must be better than all other values in S. Okay, we want to show that local IC and the monotonicity can be equivalent to global IC. So we need some notations. That W of theta hat be defined in this way. Okay, theta times V of Q of theta hat minus T of theta hat. This is what? This is the type theta consumer's utility by misreporting his type as theta hat. Okay, so my true type is here. Okay, my true type is here. And I report myself as theta hat by selecting another contract. Okay, he can do that, and once he does that, this is the utility. With this notation, global IC would just be that theta should be the best to maximize the utility in that way. If theta is globally optimal, of course it must also be locally optimal. And what does that mean? That means your optimal solution theta must satisfy the first order condition. Okay, if it is globally optimal, it must satisfy the first order condition in this sense. So this is the function to maximize. Okay, here theta is actually a constant because my type is theta. I am type theta consumer. I try to optimize my objective value according to theta hat. So that means theta hat is my variable. Theta is a parameter. Okay? So I want to maximize this function. If some value is optimal, that means the first order derivative must be 0 when I choose that value as my variable's value. Okay? So that's the first order condition. If theta is optimal, then when I plug in theta to the first order derivative, I need to get 0. So W is like this. Okay, so when you differentiate W with respect to theta hat, for the first term you need to use the chain rule because this is V of Q of theta hat. V is a function of Q, Q is a function of hat. Q is a function of theta hat. So you first have V prime of something, and then you differentiate Q with respect to theta hat. For the second term, it just goes to T prime. And then I plug in theta hat as theta. I should get this. Okay? So this equation would be called our local IC constraints. Local IC constraints. If theta satisfies this equality, it does not guarantee that it is optimal. Okay, it is just locally optimal. Okay, just like you have something like this. Here you have a point whose first order derivative is 0. And this is necessary, but it does not guarantee that it is optimal. First order condition is just necessary. Okay, but anyway, that's local IC. And we also have monotonicity. We want to show that this plus this equals the set of global IC constraints, or in a sense that we want to show you that local IC constraints are the only set that is necessary. Okay, so to show that this and that are the same, we need to show that local IC plus monotonicity can imply each constraint in the global IC set. Or the other way, with global IC, we can prove local IC and the monotonicity are true. The first one, from right to left, is very obvious. So first, by definition, if something is globally optimal, it must be locally optimal. Okay, according to our derivation in the previous slide, by definition, this is true. Also, in step 1, we have shown that if you have all those IC constraints, then you can have monotonicity. Okay, so this part is done. Now let's work on the second part. Suppose that's false. Suppose that's not true. That means I can find a type theta where there is a reason to lie. Okay, so that guy would find reporting theta hat is better than reporting theta. Okay, for some theta hat, I don't know, but anyway, that guy finds this is the benefit of telling the truth, this is the benefit of lying, and I want to show that I want to show that this is impossible. I'll say it again. I assume that I have local IC, I assume that I have monotonicity, but I assume that I do not have global IC. If I do not have global IC, I should be able to find theta and the theta hat for this to be true. So without loss of generality, that theta hat to be greater than theta. If that's not the case, we just need to reverse their notation. So now our theta hat is greater. In that case, we have the following relationships. Okay, this is the quantity that we are interested in, and we claim that it is positive. And now for this one, the second argument is the variable. So we can rewrite the difference into this. Okay, the variable is x. We find its derivative. We find its slope or derivative, and then we do an integration from the lower part to the upper part. If you need some kind of reference, then this may help. Okay, recall yourself that if you want to calculate fa minus fb, then what can you do? You can do an integral from for f of prime of x from a to b. Okay, and this is exactly the theorem of calculus. You have f, you differentiate it, and then integrate it. You're going to get itself, and then plug in the upper bound and the lower bound. And this is exactly the same thing here. And then when we have this can be done, right? In the previous page, we have shown this to you. this is what you get if you differentiate w with respect to x. And for here, now I replace theta by x. Okay, x is some value within theta and theta hat. If theta hat is greater than theta, then x is also greater than theta. And I know the whole term here would going to become larger when theta becomes x. Why is that? Because this and this, they are all non-negative. V prime is the slope of v. V is your utility, the part of your concave utility function. So v prime is positive. Okay? And the q prime is non-negative. Why do you know that? Because you assume that you have monotonicity. So that's why this is fine. That's why this is fine. You have monotonicity so that you have this inequality. Lastly, I now claim that this is just 0. Why is that? Because this part is just your local IC. And for any x, this is 0. So the integral would also be 0. Okay? So with monotonicity, you have this inequality. And with local IC, you establish that this is 0. And then that's a contradiction. You claimed that this is positive, but actually this must be non-positive. So that's a contradiction. You cannot find this, and local IC and the monotonicity is enough to imply global IC. Okay? Okay, so that's step 3. Now let's continue in the next video.